This video will be a review of Txy and Pxy diagrams. If you are comfortable with these topics, you can probably skip this video or watch it on double time. Remember that a Txy diagram plots temperature on the y-axis versus x and y, which are the mole fractions in the liquid and vapor phases respectively, on the x-axis. Importantly, the Txy is for a fixed pressure. So P is set for a Txy diagram. In this particular Txy diagram, we're talking about benzene toluene system at 1 atmosphere. In the Pxy diagram, it's very closely related. Pressure is on the y-axis. X and y are still on the x-axis. And for a Pxy, temperature is set, so vice versa. So you can use the Pxy and the Txy diagram to verify that the information is correct. So for example, at 1 atmosphere, I can use the Txy diagram to determine what the boiling point of pure benzene is. So that's the first piece of information you can get off of the Txy diagram. You get the pure component boiling points off of this diagram. So at the very ends where I have 1, I'm looking at mole fraction of benzene. Pure benzene boiling point is equal to 80 degrees C, roughly, by looking at the diagram. Over here, on the other side, I got pure toluene boiling point is about 110 degrees C. I can go to 1 atmosphere and that temperature. Actually I can't. So I have to do 100 degrees. So if I wanted to compare between the two, or you know what, I'm going to get to that a little bit later. On the Txy diagram, the top region corresponds to vapor. So don't ever memorize that. Just remember that the top of the diagram corresponds to high temperature. The bottom of the diagram corresponds to low temperature, so this is the liquid region. The way you read these diagrams is that if you're outside the phase envelope, you have two phase regions. I'm sorry, one phase region is outside the envelope, and the two-phase region is inside. So if I am inside the two-phase region and I have a composition of, let's say, 60% benzene and a temperature of 93 degrees C. So if this is my composition and my temperature, I can draw a horizontal tie line across, and this would give me my compositions of my liquid and my vapor phases. So draw straight lines down to read what the compositions are. And use your intuition to tell you which one is which. So for instance, the point on the dew point curve, which is the one that's next to the vapor. So I need to label that as well. This is going to be my vapor composition. So this is Y benzene there. And the one that is in the other one, the bubble point curve, is my mole fraction of benzene in the liquid phase. So X benzene is there. So I don't have enough space to draw, but remember this is called a tie line, this horizontal line. Remember that I can't exist inside the two-phase region. So anytime that my coordinates would be within the two-phase region, I draw that horizontal tie line and my compositions are linked. Over on the Pxy diagram now, you can get pure component vapor pressures. So over on the right-hand side, I've got pure P star, pure benzene, P set at 100 degrees C is equal to 1330 mmHg, and pure toluene P set at 100 C is equal to 560 mmHg. So what I was saying earlier is you can use the two diagrams. If you have both, you can use them to verify the information. So therefore at 100 C and 1 atmosphere is where I have the same information. So on my Pxy diagram, if I look at 1 atmosphere, which is 760, and I draw in my lines like this. Also, for the PXY diagram, it's flipped in terms of which one's vapor and which one's liquid. Again, don't memorize that. Just remember that at high pressure, you're more likely to be a liquid. And at low pressure, you're more likely to be a vapor. Therefore, the bubble point and the dew point curves are also flipped. So the one that's also always close to the liquid is the bubble point curve. And the one closest to the vapor is the dew point curve. They have the same name, but just different locations. So if I trace my 760 mmHg, which is 1 atmosphere, I should obtain the same mole fractions as 100C. So if I draw 100C across like that, and I'm measuring what my compositions are, I should see that at 100C, 1 atmosphere, I've got a Y benzene of 0.45 or so, and an X benzene of 0.24, we'll say. So looking over to the other diagram, my line's a little bit crooked. The answer should be the same. It doesn't look like it, but I drew it a little bit off. Sometimes it's hard to read these diagrams too and draw straight lines. Same answer here. So I've got X benzene at 0.24 roughly. If I draw my tie line, Y benzene at about 0.45. So you can use these as figuring out what your composition of liquid and vapor phases that are in equilibrium with each other. Now, these are how TXY and PXY diagrams looked in MEB, where we were always assuming ideal. If you cannot assume ideal, then oftentimes you'll have a PXY diagram that looks like this. So this is an example of a TXY diagram for the ethanol benzene system. You see immediately ethanol benzene at 1 atmosphere, so 1.013 bar. Immediately, it looks very, very odd. You can still tell where the pure component boiling point is. So this is pure ethanol boiling point. And that is equal to, oh, decimals on the graph are going to be hard to read. Maybe 78 degrees C. And pure benzene boiling point is maybe, let's see, halfway between 77.5 and 82.5. Call it 80. And ethanol benzene are two molecules that look very dissimilar. So benzene is a 6-membered ring with double bonds. Ethanol is 2 carbons and an alcohol group. So you can tell just by looking at the shape of the molecules that it's likely to behave very non-ideally. How much non-ideally is very surprising. So even though the molecules look rather different, their boiling points are the same. Yet, if you look at the boiling temperature of the mixture, all the boiling point temperatures are outside the range of 78 to 80 C. And in fact, this point here where they come together is a special point. This is called the azeotrope. And so we would say that the ethanol benzene system forms an azeotrope at whatever temperature this is. They didn't label this. I would have to assume that it is 87 or 67.5. At 67.5 C and 1 atmosphere and 43% ethanol, you would form an azeotrope. Azeotrope means that the liquid and vapor compositions are the same. Compositions are equal in equilibrium. And this represents a problem from the standpoint of separations, because usually if you wanted to separate two components, you could boil a liquid and obtain a vapor that has a different mole fraction. But if you boil this liquid that is 43% ethanol, you're going to get a vapor that is also 43% ethanol, and therefore you cannot separate them. So we're going to talk a lot about how these azeotropic TXY diagrams come to be. You can model this by amending Raoult's law just a little bit. So instead of Raoult's law being YA times P is equal to XA P star of T, you just add a couple more terms and you have an activity coefficient model is what it's called, and you can model this. And in separations, we'll talk about what you do with this TXY curve, but just in general, the rules are all the same. So say you start off with a mixture that is 20% ethanol at 50 C, so somewhere down here, and you slowly heat. Same rules. When you get to 72.5 C, for example, you still draw your horizontal tie line, and you can still draw these lines straight down. The green curve is still the dew point curve, and the blue line is still the bubble point curve. If you have trouble remembering that, just remember that if you start with a liquid, what you would start with if you were down at this part of the curve, and you slowly heat it, the first time you reach this blue curve, the equilibrium region, would be the first bubble of vapor that you form. Vice versa, if you have a vapor and you slowly drop the temperature, the first droplet of liquid or the first dew would occur when you hit the green line. So you can still use this TXY diagram to figure out what your mole fractions of ethanol and therefore your mole fraction of benzene is. Sorry, this is X ethanol. And the only weird part is if you are on this on the right side of the azeotrope, then your Y ethanol will be less than your X ethanol. So on the left-hand side, for low ethanol compositions, for low ETOH compositions, Y ethanol is greater than X ethanol. But for high ethanol compositions, the opposite is true. Y ethanol is less than X ethanol. This is going to be important not only in this class, but in separations as well, because we typically designate one of the components as the more volatile component. In other words, volatile means that the mole fraction is more likely to be higher in the vapor phase. So volatile means likely to vaporize. And when we're talking about separations problems, we oftentimes talk about the more volatile component. So the one with the higher vapor phase mole fraction. Interestingly enough, which one is the more volatile component switches for an azeotrope. So again, ethanol is more volatile for lower compositions, but ethanol is less volatile for higher compositions. That's all for this video. In the last video, I'm going to repost the video I made in MEB, which is about how to draw TXY and PXY diagrams in Microsoft Excel.